Okay, we're about to dive into a puzzle so deep, so profound, it actually threatens to break our understanding of reality itself. And no, this isn't just about distant stars. This is a cosmic mystery that gets to the very heart of information, time, and the fabric of the universe.
I want you to think about this for a second. What if something could not just hide the past or scramble it up, but completely, utterly erase it from existence? That is the absolutely mind-bending question at the center of the black hole information paradox.
So, welcome to what is basically the universe's ultimate crime scene. The victim here? Well, it could be the law of cause and effect itself. Our job today is to investigate this spot where our most fundamental, most trusted laws of physics just completely fall apart.
And here it is, our prime suspect, a black hole. We usually think of it as a one-way door in the universe. Once you cross that boundary, the event horizon, nothing gets out, not even light. It's supposed to be the perfect vault, or so we thought.
Now, any good detective story has conflicting witnesses, right? Well, in this case, our witnesses are the two gigantic pillars of modern physics, and the problem is they're telling us completely different stories about what happens inside that vault.
And here's where it all gets messy. On one side, you've got Einstein's general relativity. It tells us a black hole is a super simple object. It takes anything that falls in, the history of a star, the words in a book, you name it, and just crushes it into oblivion. But on the other side, you've got quantum mechanics, which has this one unbreakable golden rule. Information is eternal. You can scramble it, you can rearrange it, but you can never, ever truly destroy it. These two theories are in a head-on collision. They can't both be right.
Think of it like this. If you burn a book, the story seems like it's gone forever, right? But in theory, and this is the key part, if you could somehow track every single particle of smoke, every speck of ash, you could piece the entire book back together. The information is just scrambled, not deleted. Quantum mechanics is built on this principle.
For decades, this was just a theoretical debate, something physicists argued about. But then, in the 1970s, Stephen Hawking came along and just dropped a bombshell that turned this from a debate into a full-blown paradox, forcing everyone to confront this contradiction.
What Hawking figured out was absolutely shocking. Black holes aren't eternal prisons, after all. They have a temperature. They glow with a faint radiation, and over unbelievably long periods of time, they actually shrink and completely evaporate. We call this Hawking radiation.
So how in the world does that work? Well, it's pretty wild. Empty space isn't really empty. It's fizzing with these virtual particles that pop into existence and then vanish almost instantly. But right at the edge of a black hole, one particle from a pair can fall in while its partner escapes. That escaping particle becomes real, and it robs the black hole of a tiny, tiny bit of its mass. Now do that again and again for eons, and eventually the black hole just radiates itself away to nothing. And this is the paradox. Hawking's math showed that the radiation escaping is completely random. It's just heat. It carries absolutely zero information about all the stuff that fell into the black hole in the first place. So, when the black hole is finally gone, all that information is gone with it. Poof! And that directly, violently breaks the golden rule of quantum mechanics. Physics was officially broken.
Okay, so you can't just leave a fundamental law of physics broken on the floor. That's a crime you have to solve. For the last 50 years, the smartest people on the planet have been trying to figure this out. So let's take a look at the main suspects, the leading theories for where the information went.
The investigation has really boiled down to three main lines of inquiry. And trust me, each one is more mind-bending than the last. We've got something called the holographic principle, the really radical idea of firewalls, and this truly bizarre connection known as ER equals EPR. First up, the holographic principle. This idea suggests that the information never actually makes it into the 3D inside of the black hole. Instead, it gets sort of imprinted and stored on the 2D surface of the event horizon. So in this picture, the black hole is kind of like a hologram, where all the complex info for a 3D object is actually encoded on a flat 2D surface. All right, next we have a much more violent solution, the firewall. This theory says that when you get to the event horizon, you don't just gently float across like Einstein predicted. Oh no! Instead, you slam into a blazing wall of high-energy particles. This firewall would basically incinerate anything falling in, instantly encoding its information and blasting it back out as part of the Hawking radiation. So as you can see, each of these solutions just creates a brand new problem. Holography saves the information, sure, but it gives us no clear way for that information to ever get back out. And firewalls, they get the information out, but they do it by completely trashing one of Einstein's most cherished principles, the idea that crossing an event horizon should be, well, totally uneventful.
But what if the solution is even stranger than all of that? I mean, way stranger. This brings us to our third suspect, a wild idea called ER equals EPR. It's a proposal for a deep, hidden link between two of the weirdest ideas in all of physics: wormholes and quantum entanglement.
You've probably heard of quantum entanglement. It's what Einstein famously called spooky action at a distance. Two particles that are mysteriously linked no matter how far apart they are. And wormholes are these theoretical tunnels through space-time. This idea, ER equals EPR, suggests these aren't two different things. They're actually the same thing, just viewed from two different angles, one from quantum mechanics and the other from general relativity.
So what on earth does this have to do with our mystery? Well, the implication is just staggering. It suggests that the information that falls into a black hole gets entangled with the radiation that leaves it. And according to ER equals EPR, that spooky quantum connection literally creates a microscopic wormhole, allowing the information to tunnel out and escape. It's a jailbreak at the quantum level.
So which is it? A hologram? A wall of fire? A quantum tunnel? The honest answer is, we just don't know. The case is still very, very much open.
And that's why this matters so much. This isn't just some weird puzzle about a distant object. The information paradox is a crack running right through the foundation of physics. It is the absolute proof that our two greatest theories of reality, general relativity and quantum mechanics, are incomplete. Ultimately, to close this case file, we're going to need something brand new. A grand, unified theory that can describe both the massive gravity of a black hole and the weird rules of the quantum world in one single, beautiful framework. This is the holy grail of modern physics, a theory of quantum gravity. And just think about the stakes here. If information can truly be lost forever, then the link between cause and effect is broken. The present wouldn't contain all the information from the past. This one paradox forces us to ask what space, what time, what reality itself even is. The very same laws that say information has to be conserved are what give time its direction, what makes the past different from the future. So if a black hole really can delete information, it isn't just erasing the past, it's threatening the very arrow of time itself. And that is a mystery that affects every single one of us.